So far, we've just introduced unitary operators by proving that they don't change the length of a vector. So we know what they don't do, but what do they do? Unitary operators do two things for us. First, they allow us to change coordinate systems, or more generally, what we would call representations. We could have written out a vector representing some quantum mechanical state using, say, an energy eigenfunction basis. Then we might decide that instead we wanted to represent it using some different basis. We could then use a unitary operator to change the vector from one basis, one coordinate system, to another. In ordinary geometrical space, a unitary transformation or a unitary operator can change us from one set of coordinate axes to another, for example, by rotating them. The second thing that unitary operators do for us in quantum mechanics is generally allow us to change the state of the quantum mechanical system. The state of the system presumably remains normalized as we do so, so the operator that does this change must preserve this normalization, and hence it's a unitary operator. The operator that gives us the time evolution of a quantum mechanical system is also a unitary operator, for example. So let's look at how this mathematics works.
So let's look at this unitary operator that is going to change the representation of some vector. So we suppose we have a vector or a function, and we're going to call that f old here. And it's represented on some basis, psi n, and when we do that, we get a set of expansion coefficients, c1, c2, and c3, and that will be a column vector, as usual for a ket vector. These numbers are just the projections of this vector, f old, onto these orthogonal coordinate axes in the vector space. And those coordinate axes are labelled with these kets, psi1, psi2, psi3. Suppose then we want to represent this vector on some new set of orthogonal axes, and we'll label these with another Greek letter, phi. So this is phi1, phi2, phi3. These are orthogonal axes, and these are the unit vectors, as usual, on those axes. Changing the axes, which is equivalent to changing the basis set of functions we're going to use, does not change the vector we're representing. We're merely changing the coordinate axes, if you like. We're not changing the vector. But it does change the column of numbers we're going to use to represent the vector. So it's the same vector, f old, we've started by calling it, but we're representing it on this basis, the phi basis, instead of the psi basis. For example, suppose the original vector, f old, just happened to be actually the first basis vector in the old basis, psi1. We could always have chosen that. It might seem odd to do that, but we've got good reasons for it. Then in this new representation we're going to choose with the phi vectors as the basis, the elements in the column of our numbers would be the projections of this vector, psi1, on the various new coordinate axes, each of which is simply this number, the inner product of phi m with psi1. So for the mth new coordinate axis, this is the number that gives us the projection onto that axis, phi m. So under this coordinate transformation then, or this change of basis, what used to be a vector that was 1, 0, 0, and so on, because this was our f old, was psi1, is now going to turn into a vector with the following numbers in it, the following expansion coefficients, if you like. Simply these projections of psi1 onto each of these new coordinate axes. We could do similar transformations for each different basis vector in our old coordinate system. And we get the correct transformation if we define a complete matrix made up from these vectors we constructed before for each of these. And the matrix elements in here then are simply phi I inner producted with psi j for the ijth matrix element. So that's just following the same logic we just took, but going through each different old basis vector and expressing it in the new ones. And hence, with that, we can define our new column of numbers to represent any arbitrary vector here. We started out with some specific f old. We're going to get an f new, which will be a new column of numbers. So how we do that is, whatever was the old vector, we operate on it with this unitary transform, and we get the new one. And we saw explicitly that that happened for each one of the basis functions of the old system being this vector here. And we're just adding up all of those to get the new vector over here. So this is how we transform from the vector expressed in the old coordinate system to the vector expressed in the new one. We use this unitary transformation with these numbers as the matrix elements in the unitary matrix. Note incidentally that here f old and f new are the same vector in our vector space. If you like, in our geometrical analogy, these two vectors are pointing in the same direction and are the same length. They are the same vector. Only the representation, the coordinate axes, and consequently the column of numbers we're going to use, has changed, not the vector itself. Now we can prove that this operator we've just constructed, u, is a unitary operator. So we'll write the matrix multiplication in its summation form. So the matrix multiplication of u dagger, that's the Hermitian adjoint of our unitary operation u, times u would be this product, and we're going to take the ijth element of that. Well, if we write that out in the summation form for working out matrix multiplications, then that just corresponds to the sum over m of umi star umj. This is the imth element of u dagger, but the imth element of u dagger is the complex conjugate of the mith element of u. That's why this is this element. Of course, we can work each of these out. We know that umj was just phi m psi j, and umi was just phi m psi I, so umi star is just the complex conjugate of this number. Now, the complex conjugate of an inner product is the same thing as the Hermitian adjoint of an inner product, because an inner product is just a complex number. That's a 1-by-1 matrix, and for a 1-by-1 matrix, the complex conjugate and the Hermitian adjoint are the same thing. Also, we know in general that if we take an inner product and swap it round into the other direction here, we take the complex conjugate when we do that. Anyway, whichever way you want to look at it, this with the complex conjugate turns into this. Now we notice that buried in here is actually an identity operator. This is psi I out here, this is psi j out here, so there's nothing of these two that sums over m. So we can move that summation over m inside here, and that's what we've done in this next line. And this, of course, we recognize is just an identity operator, because this set of phi m's is presumably complete. An identity operator does nothing, so we can take it out. So what we're looking at is the inner product of psi I and psi j. And of course, that's just the Kronecker delta, because these are orthogonal and actually orthonormal functions. So that means that since we get this for every single one of the elements in this product here, what we have actually is a diagonal matrix with ones down the diagonal. And that just means that the product of u dagger times u is equal to the identity matrix. So that means that u is unitary, because its Hermitian transpose, the u dagger, is behaving as its inverse, and that's a definition of a unitary matrix. Hence, any change in basis can be implemented with a unitary operator. We can also say that any such change in representation to a new orthonormal basis is just a unitary transform. Note incidentally that it doesn't matter which way round we do this multiplication, u dagger is the same thing as the Hermitian adjoint of u dagger u, which is therefore the Hermitian adjoint of the identity operator, which is just the identity operator. So the mathematical order in this multiplication makes no difference.
Now remember that we concluded above that a unitary transform does not change any inner product. We can now therefore also conclude that a transformation to a new orthonormal basis does not change any inner product. Again, this is what we would have expected from thinking about the inner product being like a vector dot product of two geometrical vectors. Of course, such an inner product does not depend on the coordinate axes, only on the directions and lengths of the vectors themselves. If a unitary operator can change a vector from being represented on one coordinate system to another, can it do the same for operators? Remember, an operator, when written as a matrix, has matrix elements that depend on the basis we used. If we change to a new basis, we will obviously then have to change the matrix elements. Can the same unitary matrix that we use to change the representation of vectors, to change them from a new coordinate system, for example, can that also be used to transform other operators to new coordinate systems without us having to recalculate all the matrix elements again? The answer, of course, is that it can. If we know all the matrix elements on one basis, we will be able to use the same unitary matrix, the one that we used to change the vectors to a new basis, also to change the operators to the new basis, without recalculating all the matrix elements. Let's see how this works.
Consider a number such as the bra vector g, some arbitrary function, and an operator a, and the ket vector f. And the result of this operation should not depend on the coordinate system. After all, this is a vector. We operate on it to change its length and its direction, as it were, and then we take the inner product of that new vector with this one. It should not depend what basis we're using to represent any of these. This number should be the same number if these are the same vectors and this is the same operator, the operator that does the same thing to a given vector. So the result of this in some old coordinate system should be the same as in the new coordinate system. So therefore, however we get to this answer here in the new coordinate system should be the same as the answer in the old coordinate system. Note that the subscripts old and new refer to the representations, not to the vectors or the operators themselves. We're saying the vectors are really the same vectors and the operators really the same operator. It's just the way we're writing them down that is different between this expression and this expression. Only the numbers that represent these vectors and this operator have changed, not the vectors themselves and not the operator itself. Well, with our unitary operator u to go from old to new systems for vectors, we figured that out, we can write the following. We can take our bra vector for g new, we can turn it into a ket vector with a Hermitian adjoint. And then we know how to write down that ket vector, g new, in terms of the old version of that ket vector. That's just u operating on g old. And similarly, the new f is just u operating on the old f in terms of the columns of numbers. Well, having written this down this way, we can take the Hermitian adjoint of this product, which means flipping it round, so that gives us a bra vector g old and u dagger from taking the Hermitian adjoint of this product. Now, we believe that this new version should be the same number as this old version. So therefore, we believe that this here must actually be the same as that there. Hence, we identify that this u dagger a new u must be a old. Or we can change that round. We can pre-multiply by u and we can multiply by u dagger on the other side here on this expression and similarly on this one. So on this expression here, the u would give us u dagger, and the u dagger over here would give us u dagger. And, of course, u dagger is just the identity operator. So this gives us a new. So simply rewriting that then, the operator on the new coordinate system is related to the operator on the old coordinate system in the following way. Incidentally, we can understand this. So now we're talking about an operator in the new coordinate system. Therefore, if we're coming along with a vector in the new coordinate system and we're multiplying by the u dagger here, what this u dagger is doing is it's taking our vector in the new coordinate system and turning it into one in the old coordinate system. Then we operate with the operator in the old coordinate system to get a vector in the old coordinate system, and then we use u to transform from the old coordinate system back to the new coordinate system. So that's what's going on inside here, and of course that's just the same thing as operating with a in the new coordinate system. So this is how we transform an operator from an old coordinate system to a new one.
We've just been looking at unitary operators that change the coordinate system, but not the actual vectors or the operators. So here is our vector, here is our coordinate system, and we've been saying we use a unitary operator to change the coordinate system, but the vector itself remains the same. So we've been using these unitary transformations to change the way we're writing down these vectors or operators. But they're still the same vectors, and the operators still do the same things to the vectors as they did before, rotating the vectors and stretching them essentially. Remember that what an operator does to a vector is it turns it round and possibly stretches it or compresses it. And of course, in quantum mechanics, we have to remember we have complex numbers involved with this. As we said before, operators that change the quantum mechanical state are also unitary. Why such operators arise in quantum mechanics is simple. If we're working, for example, with a single particle, then the sum of all of the occupation probabilities of all the possible states is unity. It's important to understand that such operators are not changing the basis set. They're actually changing the quantum mechanical state of the system, and hence they're changing the vector's orientation in space. So operators that are changing the quantum mechanical state are rotating this vector. They're not changing the length of it because that's staying the same, but they're rotating it around in some way to say we're in a different quantum mechanical state, but we're on the same coordinate system. As a minor mathematical confusion, there's no difference in the notation we use when we're using a unitary operator to change coordinate systems and when we're using it to change the physical state of the system. As far as the mathematics is concerned, these are both just unitary transformations. However, remember that using a unitary operator to change a coordinate system or basis is a purely mathematical operation. There's no change in the physical state. So here's our physical state. We're rotating the coordinate system, but we're not changing the physical state with that kind of unitary operation. Using a unitary operator to change the quantum mechanical state of the system is different. It's rotating the vector in Hilbert space while leaving the coordinate axes unchanged.
So, in thinking about a unitary operator that changes the state vector, for example, if our quantum mechanical state psi here is expanded on some basis psi n, so our state psi is a sum over n of some expansion coefficients an times psi n, then of course the sum of the squares of these expansion coefficients is going to be 1 because our quantum mechanical state psi was presumably normalized. And if the particle is to be conserved as we go forward, then this sum of the modulus squares of the expansion coefficients should not change. It should be retained as the quantum mechanical system evolves in time. That is, really, the length of this vector should be retained. This here is just the square, of course, of the vector length. It's bra psi times ket psi, if you like. Hence, a unitary operator, which conserves length, will describe changes in the quantum mechanical state that conserve the particle. They conserve the probabilities all adding up to 1.